The Zoche Aero-Diesel is an air-cooled, two-stroke, supercharged and turbocharged radial diesel aircraft engine aimed at the light aircraft engine market, and it's a pretty impressive design. The Aero-Diesel can almost be seen as the revival or perhaps the completion of an engine that emerged in the early 1930s, which was at the time frequently described as revolutionary. But despite breaking a few records, that engine ultimately failed and production was stopped a mere 4 years after going on sale. That engine was the Packard DR-980, an air-cooled, diesel-powered radial aircraft engine. I've covered the DR-980's design and history in this video, but in short, it failed largely due to insufficient development time and arguably because of the choice to run a 4-stroke cycle instead of a 2-stroke cycle. The DR-980's claim to fame came down to 4 main points. 1. It was the first certified diesel aircraft engine, made possible due to its unique lightweight design. 2. It ran on diesel fuel, which has a much lower fire hazard than petrol or F-gas, something that was a serious concern in early aviation. 3. It boasted significantly better fuel economy than its gasoline-powered counterparts. And 4. It produced no electromagnetic interference with onboard radio equipment. This was due to the absence of a spark ignition system, enabling clear in-flight radio communication for the first time. There were other selling points too. For example, it was claimed to be highly reliable due to the low number of moving parts. But in reality, that reliability never fully materialized. It was also marketed as being well suited for aerobatics, as its direct fuel injection system wasn't affected by inverted flight or negative Gs, and it also didn't suffer from carburetor icing, as it didn't have a carburetor. These were the proverbial bullet points you might have found on the PowerPoint slide promoting the DR-980. But in reality, the engine was plagued by issues, most notably reliability, largely stemming from the lack of proper development. The engine's decline was hastened by the rise in aviation gasoline octane ratings, which allowed petrol engines to achieve better power and efficiency. At the same time, improved electromagnetic shielding and radio filtering technology resolved radio interference issues on gasoline-powered aircraft. Together, these developments erased most of the DR-980's advantages. So while it earned a few headlines and set a few records, it ultimately became little more than a footnote in aviation history. A few decades later, in the late 1980s, Zoche began developing a diesel radial engine for light aircraft, and interestingly, it seemed like they were singing from exactly the same hymn sheet as Packard in the 1930s. Their listed benefits? No electromagnetic interference, an issue that had already been resolved in gasoline engines back in the 1930s. A reduced fire hazard, always a factor, but hasn't been a major deterrent to petrol engines in decades. Claimed good reliability due to fewer moving parts, just like with the Packard DR-980, although in that case the promise didn't quite live up to reality. They also touted full aerobatic pressure lubrication, which was a selling point for the DR-980 as well. Even no rubber hoses made the list, a benefit also cited for the DR-980, though in that case it was due to the engine's harsh vibration. It's almost like they dusted off that same PowerPoint slide from Packard in the 1930s and used it to promote their new engine in the 1980s. Now, I say all this a bit tongue-in-cheek, because the Aero-Diesel's design is in fact quite impressive. There's far more going on here than first meets the eye, and it deserves a closer look. So I hope you have a cup of tea or coffee nearby, because there is a lot to unpack. Let's get one thing out of the way first. To the best of my knowledge, the Aero-Diesel engine's development started in the late 80s, with engine testing starting in the mid-90s. Then, this bench test video appeared on YouTube in 2015. It was followed by an update in 2019 and then complete silence. As of now, it's unclear whether the engine is still in development. This video isn't about when or even if the Aero-Diesel will reach the market. It's about the engine's design and how it tackles several long-standing limitations of piston aero engines with remarkable cleverness. The brochure lists 3 main engine variants, a 4-cylinder producing 150 horsepower, an 8-cylinder delivering 300 horsepower, and a 2-cylinder half-radial or V layout generating 70 horsepower. I believe the V-twin will be an excellent addition to the market for ultralight and light sport aircraft, but in this video I'm focusing primarily on the 4 and 8-cylinder radials. All 3 share a compression ratio of 17:1, which contributes to their good fuel efficiency. For example, the 150 horsepower model consumes only 21 liters per hour at 75% cruise power, an impressively low figure. Fuel consumption for the 70 and 300 horsepower variants is similarly efficient, and specific fuel consumption numbers seem to confirm the low fuel burn. At first glance, the engine weights might seem unremarkable. However, for a diesel, these weights are quite competitive, comparable to gasoline engines like the Rotax 915 and 916, which would be direct competitors to the 4-cylinder Aero-Diesel in the light aircraft market. Being air-cooled means you don't need to factor in an additional 7 to 15 kilograms associated with coolant and radiator systems, so the dry weight of these engines certainly is favorable. One might be tempted to compare the 150 horsepower version of the Aero-Diesel to the Rotax R3600, a modern 3.6 liter air-cooled, geared, gasoline-fueled 9-cylinder radial engine. While both produce the same horsepower, the Aero-Diesel is significantly lighter and benefits from forced induction. The Rotax, being naturally aspirated, would be outperformed across the board, especially at altitude where the turbo and supercharged diesel maintains power while the Rotax suffers from density altitude losses. The Rotax also burns 27 liters per hour at 75% power, about 30% more than the Aero-Diesel. So it's not a direct competitor to the Aero-Diesel when considering overall performance, weight and fuel efficiency. While the Rotax would seem to occupy the same radial niche in general aviation, it doesn't really, as these would typically power vintage-type planes and replicas and not the modern light aircraft which the Aero-Diesel targets. The 300 horsepower variant's power-to-weight ratio surpasses that of most comparable engines available on the market today. Displacement of these engines is larger than one might initially expect, especially given their relatively low weight. While not as massive as air-cooled Continentals or Lycomings, the 4-cylinder Aero-Diesel displaces nearly twice as much as the Rotax engines. This makes sense because it's a direct drive engine designed to produce maximum power at a low 2,500 RPM. You might have noticed something unusual about the Aero-Diesel engines, especially if you're familiar with radial engines, which is that all 3 variants have an even number of cylinders, 4, 8 and 2. This is notable because radial engines traditionally have an odd number of cylinders per row. Why is this? The main goal, especially for aero engines, is to achieve an even firing interval throughout its running cycle. An even firing interval ensures smoother power delivery to the reciprocating and rotating components, including the propeller. A full 4-stroke cycle requires 720 degrees of crankshaft rotation. Each cylinder fires once every 720 degrees, meaning it fires every second time the piston reaches top dead center. Radial engines with an odd number of cylinders, say 7, achieve an even firing interval by firing every other cylinder in sequence. For example, the firing order would be 1, 3, 5, 7, 2, 4, 6, and then back to 1. This results in a consistent firing interval. On a 9-cylinder radial, that interval is 80 degrees. On a 7-cylinder, it's 103 degrees, and on a 5-cylinder, it's 144 degrees. These intervals are evenly spaced, providing smooth running. But what happens with an even number of cylinders on a radial, such as 4? To achieve an even firing interval, you would need to fire a cylinder every 180 degrees of crank rotation. Starting with cylinder 1 at TDC, 180 degrees later would be cylinder 3. But another 180 degrees later is again cylinder 1 without having fired 2 or 4. Attempting a firing order like 1, 3, 2, 4 creates uneven intervals of 180, 270, 180, 90, which leads to a rougher running engine. Now, here is the difference. The Aero-Diesel engines are 2-stroke rather than 4-stroke. This means each cylinder fires once every 360 degrees of crankshaft rotation. That is, every time the piston reaches top dead center. To achieve an even firing interval on the 2-stroke 4-cylinder engine, a cylinder needs to be fired every 90 degrees of crank rotation. Starting with cylinder 1, 90 degrees later, piston 2 reaches TDC and can be fired. After another 90 degrees, cylinder 3 is at TDC and can be fired. And another 90 degrees later, cylinder 4 can be fired. This yields a perfectly even firing interval. So, because the engine is a 2-stroke, the traditional requirement for an odd number of cylinders in radial configuration is eliminated. Furthermore, being 2-stroke doubles the frequency of power strokes compared to a 4-stroke. This results in increased power stroke overlap and smoother overall operation. The same principle applies to the 8-cylinder engine. This potentially allows for even better smoothness with a firing interval of 45 degrees. The Aero-Diesel engines are touted as having unusually small frontal areas. That might sound strange at first because radial engines are typically known for very large cross-sections. This makes them generally unsuitable for most modern light aircraft. So how is it that the Aero-Diesel can claim to have a compact frontal area? And no, they're not exaggerating. If you look at the published dimensions and compare them to popular aero engines, it seems true. This is even more surprising considering we already know the displacement of these engines is relatively large. Here's how they've done it. In a typical radial engine, adding more cylinders to a single row increases the crankcase diameter because the cylinders need some clearance. More cylinders per row equals bigger diameter equals larger frontal area. For example, a 7-cylinder radial generally has a larger frontal area than a 5-cylinder and a 9-cylinder larger than a 7-cylinder. This is precisely why most historical radial engines maxed out at 9 cylinders per row. Beyond that, the engine becomes unreasonably large. So instead, designers would keep the max amount of cylinders per row at 9 and add more rows of cylinders behind the first. Zoche took that logic to the extreme. Their 8-cylinder engine doesn't use a single wide row of 8 cylinders. Instead, it's built as a twin-row radial, 2 rows of 4 cylinders. By doing this, the frontal area is kept much narrower. But what about the 4-cylinder single-row radial? Even with just 4 cylinders, you'd expect a radial to be somewhat bulky, yet it's not. That's made possible due to the thermal behavior of diesel engines. Diesel engines are more thermally efficient than gasoline engines, in part due to their higher compression ratios. More of the fuel's energy gets converted into mechanical work and less is wasted as heat. That means less engine cooling is required and cooling fins can be physically smaller. That reduces both frontal size and weight. Also, unlike spark ignition engines, diesels don't have a concentrated hot spot around a spark plug. Instead, diesel combustion tends to be slower, cooler, and more evenly distributed throughout the chamber. That leads to lower cylinder head temperatures overall and less cooling is required. The Aero-Diesel, being a 2-stroke diesel, eliminates spark plugs, valves, and the valve train entirely. That allows the cylinder head to be much smaller and simpler, further shrinking the overall engine profile. When you look at the Aero-Diesel next to a similarly powered air-cooled gasoline engine, the difference in fin size and head bulk is immediately noticeable. The Aero-Diesel's fins are minimal and the heads are compact. Put all of that together, 2 rows instead of a wide single row, modest cooling requirements, and extremely compact cylinder heads, and it becomes clear how this engine manages to keep its frontal area small. In fact, these radials could likely fit into just about any engine bay that accommodates a similarly powered Boxer 4 or 6 engine. Being a 2-stroke engine, the Aero-Diesel doesn't use conventional intake or exhaust valves. Instead, it relies on the piston itself to control airflow by covering and uncovering ports machined into the cylinder walls. From what I can tell, the Aero-Diesel uses a form of loop scavenging, likely with 2 intake ports and 1 exhaust port per cylinder. In any 2-stroke engine, scavenging, the process of clearing out exhaust gases and refilling the cylinder with fresh air, is critical. The Aero-Diesel accomplishes this with forced induction, using both a supercharger and a turbocharger together to drive air into the engine. Now, you might wonder, why not use a simpler scavenging method like cross-flow scavenging, where the intake and exhaust ports are on the opposite sides of the cylinder? Well, cross-flow scavenging has a major drawback, especially when forced induction is involved. Because the intake air is being pushed in under pressure, it can easily just flow straight through the cylinder and right out the exhaust port, wasting precious fresh air and reducing efficiency. That's why loop scavenging is the better choice here. In loop scavenging, the intake and exhaust ports are arranged in such a way that the air entering the cylinder has to travel in a looped path before it can exit. This reduces the amount of fresh intake air escaping directly out the exhaust. An additional benefit of loop scavenging is the swirl effect it generates. This air movement helps with atomizing the injected diesel fuel more quickly and thoroughly, important for efficient combustion in a direct injection engine. Based on the illustrations, it appears that the exhaust port on each cylinder is connected to a pipe leading toward the rear-mounted turbocharger. New air is then routed through a distribution manifold, likely feeding into two intake ports on the sides of each cylinder. This combined boost from both the turbocharger and supercharger not only enhances scavenging efficiency, but also helps maintain engine power at higher altitudes by compensating for reduced air density. The Aero-Diesel engine uses a dry sump lubrication system, which stores oil in a separate external tank instead of letting it pool in the crankcase. From there, oil is delivered under pressure to the internal engine components. Now, whenever I talk about inverted engines or cylinders, a common question comes up. How does it prevent oil from pooling in the inverted bottom cylinders when the engine is running? First, when the engine is running, the piston speeds are extremely high, and much of the oil that contacts the lower rotating or reciprocating components gets rapidly atomized into a mist. It doesn't have time to accumulate into a liquid pool. Second, dry sump systems are specifically designed to prevent this. Scavenge pumps are positioned in low points within the crankcase. These pumps actively collect any oil that drains down and return it to the external oil tank. From there, it can be cooled and recirculated under pressure back through the engine. And combined with fuel injection, the Aero-Diesel is inherently aerobatics capable right out of the box with no special modifications needed. We've already covered the firing interval, which is critical to smooth power delivery. But there's another major contributor to smooth running, and that is mechanical balance. And since the Aero-Diesel is claimed to be a very low vibration engine, let's look at how that is achieved. To assess mechanical balance, we first need to understand how the connecting rods attach to the crankshaft, since this directly determines piston movement and overall balance characteristics. Traditionally, radial engines use a master and articulating rod setup. One conrod, the master rod, connects directly to the crankshaft, while the other conrods connect to the master rod, not the crankshaft. This system has worked well for the last 100 years, but it comes with well-known compromises. Only the master conrod's big end traces a perfectly circular motion around the crankshaft. The articulating conrods connected not to the crankpin but to the articulating rod assembly follow elliptical paths. This results in slightly different stroke lengths and compression ratios compared to the master conrod's piston. The Aero-Diesel engine avoids this issue entirely. It uses a connecting rod design patented by Zoche, which eliminates the master and articulating setup. Instead, all four rods connect independently and directly to the crankpin, each with a single bearing face. This ensures that all pistons share identical stroke lengths and motion paths, improving symmetry and balance. It also simplifies assembly. But the innovation didn't stop there. The small ends of these conrods connect to pistons via a concave bearing surface, which matches a convex bearing surface on the piston itself. This has a clever effect. It raises the effective pivot point of the wrist pin higher up inside the piston, something not possible with conventional wrist pin placements. This results in a longer effective connecting rod, which lowers the maximum tilt angle of the conrod at mid-stroke. This reduces lateral side loading on the cylinder walls and improves the transmission of forces. I'll link to the patent in the description if you want to explore the design in greater detail. Now let's talk about balance. With a 17:1 compression ratio and a relatively large displacement, these engines must use robust and heavy reciprocating components. Even so, the 4-cylinder Aero-Diesel achieves perfect primary balance using crankshaft counterweights. Normally, counterweights mostly cancel out the rotational imbalance caused by the conrod big ends. They can't usually eliminate reciprocating imbalance and rotational imbalance. But that changes with certain engine configurations, like a 4-cylinder radial where the cylinders are 90 degrees offset. In this configuration, the same counterweight that opposes the conrod mass rotationally can also counteract reciprocating forces from pistons 90 degrees out of phase. For example, with piston 1 at top dead center, the counterweight not only opposes its inertial forces, but also counters the inertial force from piston 3. And while doing that, it doesn't neglect its main duty of balancing the conrod big ends rotationally. At this position, it opposes both piston 2 and 4's conrod big ends. How neat is that? This means one properly sized counterweight can simultaneously address both rotational and reciprocating imbalance of all 4 pistons and all 4 connecting rod big ends, something not normally possible. This applies to both the 4 and 8-cylinder variants of the Aero-Diesel. Each row of 4 cylinders has perfect primary balance. Secondary imbalance is typically a problem on radial engines. I've described the secondary imbalance many times already, but here's a video that fully describes it specifically for the radial engine. But in the quickest possible explanation, it arises due to the non-uniform acceleration of pistons caused by the tilting of conrods. This creates forces that are hard to cancel since it occurs twice as often as the primary imbalance. At any point when the conrod becomes fully tilted, the imbalanced force is downwards or in the direction of the crankshaft, and when the conrod becomes fully straight, the imbalance is upwards and away from the crankshaft. But in the Aero-Diesel's 4-cylinder layout, every piston has a counterpart exactly 180 degrees out of phase, meaning these secondary forces are equal and opposite and cancel each other out. Again, this applies to both the 4 and 8-cylinder variants. Thus, unlike a conventional radial, the 4 and 8-cylinder radial has perfect secondary balance. So, by all accounts, with even firing intervals and perfect primary and secondary balance, the Aero-Diesel may well be amongst the smoothest running piston aircraft engines. One concern that always seems to come up when discussing diesel engines is cold starts and fuel gelling. Let's start with cold starts. This is typically addressed using glow plugs, which are small electrically heated elements that assist with ignition during cold conditions. Now let's address the fuel gelling problem. This concern stems from the fact that diesel fuel can gel to the point where it won't flow below a certain temperature. But here's the reality. The fuel this engine would mostly be run on, Jet A1, doesn't gel until about -47 degrees Celsius. This is far below the temperatures encountered by piston aircraft operating at typical altitudes. This is simply not a realistic concern for most scenarios. And when using standard pump diesel, which they do state the engine can run on, gelling is prevented by a fuel preheat system. Pump diesel can begin to gel around -9 degrees Celsius, which is certainly within the temperature range a piston aircraft might experience. But preheating the fuel eliminates this problem. Like many diesel concerns, these are mostly rooted in automotive experience, not aviation-specific operation. So what exactly is the advantage here? You're looking at a compact, air-cooled radial diesel engine that's small enough to fit into the engine bay of a light aircraft designed for a Boxer 4 or 6 without requiring a complete cowl redesign. Some modifications may be necessary, particularly with air baffling, but that's to be expected. One of the most significant advantages is the low moving parts count. Remember, a part not present on the engine is a part that can't fail. Here you might point to the turbocharger and supercharger as a concern, but most of its direct competitors like the Rotax 915, 916 and Continental TSI 0520 are also turbocharged. Also, the Aero-Diesel's dual supercharger and turbocharger means if one fails, the other should be able to provide enough boost to produce enough power to maintain altitude, or at the very least enough to do a controlled descent. One part you will not find on any of the competition, however, is a supercharger. But a supercharger is likely far more reliable than a full valve train and all related moving parts. Despite being a diesel, the engine is lighter than most of its competitors. That's impressive. As for fuel efficiency, diesel's higher energy density and better thermal efficiency results in lower fuel consumption. From a smoothness perspective, the 4 and 8 cylinder Radial is inherently perfectly balanced and should run smoother than any Boxer 4 and most Boxer 6s. The targeted TBO is 2000 hours, which is on par with or better than many certified piston aircraft engines. That said, it was stated that early models may have lower intervals. Diesel engines often can't be overhauled and would typically have a TBR or time between replacement, and what they describe here sound more like a TBR than a TBO, but I can't be 100% sure. So will we ever see these engines enter full production? Was the project shelved due to unexpected development hurdles? Did one of the two dominant aero engine manufacturers pay to get the Aero-Diesel off the market? Let me know in the comments. Thanks for watching. See you in the next one.